We are in chapter 3, moving right along. Your chapter 3 or chapter 2 test is due on Monday, right? We spent a lot of time talking about parallel lines and transversals, right? So we're going to keep talking about those today, unless anybody has any questions, which I am happy to go over anything that you might have with that as well. So, anybody have any questions before we get started? No. No. All right, good deal. Okay, so we spent a lot of time talking about, like I said, parallel lines, the transversals that cut them, and what the angles mean, and what that all means. So just a super quick review. Let me pull up Paint here. So kind of pull it all together. So maybe if we say it enough, it'll kind of stick in our brains, right? All right. So we have two parallel lines, right? And they are it's like Halloween colors. We're going to cut them with a transversal line. So that just basically means another line. This could come in at any angle, right? Let me take this and copy it a few times. Oh no, you don't see anything. Maybe I should share my screen. Might help. All right, I guess I'll share with you guys. Just today. Voila. Now you can see my Halloween lines. Okay, so review time. All right. So first we're going to talk about corresponding angles. Okay, so this first one is going to have everything to do with if I spell it right, corresponding angles. Not angels, angles. We have our corresponding angles. All right, corresponding angles. So that basically means angles that are in the same spot. They correspond to each other. So for example, this angle here, if I can get this all the way, we can pick any angle. So this angle here corresponds to this angle here, okay? We have two postulates that cover corresponding angles. So corresponding angles don't get proved, they get a postulate. So postulate means we just say it's true and you just believe it, right? So we have postulate 15, P15, okay? Postulate 15 says that if you have two lines are parallel and they're cut by a transversal, then the angles are congruent. So 15 basically says if you have lines that are parallel, that's our sign for parallel, right? That just doesn't mean two. Then your angles are congruent. Your angles are congruent. This is very shorthand. Okay? Postulate 16 says if your angles are congruent, then the lines are parallel. Okay? So remember, we've got like the reverse of each one. All right, so postulate 15 says if our black and our orange line are parallel to each other, then our blue angles are congruent. Postulate 16 says if our blue angles are congruent, then our black and our orange line are parallel. Okay, so that's our first kind of set. So this is basically taking you through 3, 2, and 3, 3, a review all in one. Okay. And it's actually a little bit of 3, 1 because 3, 1 we define what is a corresponding angle and all that kind of thing. Okay. All right. Number 2, we're going to talk about over here. We're going to talk about alternate interior angles. Okay. So what is an alternate interior angle? Interior means inside, right? And alternate means opposite. So, and there's, by the way, over here on the blue one, there are 4 corresponding angles to each other. Okay. Here we have 2 different alternate interior angles. I'm just picking one for effect. Okay. So for alternate interior angles, we have 2 theorems. We have theorem 3.1, and we have theorem 3.4. Okay. So theorem 3.1 says if our lines are parallel, then the angles are congruent. And theorem 3.4 says if the angles are congruent, then our lines are parallel. All right, so if you have a problem and they tell you that the 2 brownish tannish colors are congruent to each other, right, then we can say that the black and the orange lines are parallel because of theorem 3.4. All right, or if I tell you that the black and the orange lines are parallel, then you could tell me that the 2 brownish color angles are congruent to each other. Okay. Review. Okay, so now let's go purple. Okay, purple, we're going to talk about alternate exterior angles. Alternate exterior. All right, alternate, again, opposite sides. Exterior means outside. So we got this angle and this angle. All right, if this cover alternate exteriors are covered in theorem 3.2 and theorem 3.5. Okay, these say theorem 3.2 says if our lines are parallel, then our alternate exterior angles are congruent. And theorem 3.5 says if our angles are congruent, then the lines are parallel. Kind of feels like we're talking about the same thing over and over again, right? You guys following along on there? Having fun yet? Awesome. Okay, last one. This one's actually different. So the first one's different. Corresponding angles is different because they're covered by postulates, not theorems. Alternate interior and alternate exterior are basically the same. You know, there's a theorem that covers each one. And then we have our last case, which is consecutive interior. That's hard to see. All right, so what's up with these consecutive interior guys? I don't know. We'll change it to something red. There we go. Consecutive interior angles. All right. Interior on the inside. Consecutive means they're on the same side. So these are a little bit different. Consecutive interior angles are covered by theorem. I keep forgetting THM. 3.3 and theorem 3.6. So these are a little bit different, okay? So if you have these two angles and they're supplementary, theorem 3.3 is if the lines are parallel, then the two angles are supplementary, which means they equal 180 degrees. Okay? And theorem 3.6 says if they're supplementary, if these two red angles are supplementary, then the orange and the black line are parallel. All right, so now we have a big review. You should be experts on 3.1 through 3.3 by now because we've gone over them a couple times, which is good because I think it's a good concept to do. Let's do a couple problems with this, and then I have another theorem for you. I'm sure you're so excited. I hear cheering over the phone, right? Let's turn this off. That's what we just talked about. All right, so first up we have, can you prove that lines A and B are parallel? Explain why or why not. Okay, so if you know this, you can type it in the chat. We have that the measure of angle 1 plus the measure of angle 2 equals 180 degrees. So that should set off like alarm bells in our head that equal 180 degrees. That's supplementary angles, right? So measure of angle 1 plus the measure of angle 2 equals 180 degrees. That means that 1 and 2 are supplementary angles, right? And what do we know about supplementary angles? That they're awesome? They're so much fun? No, we know that, right? We know that if two lines are cut by a transversal and the consecutive interior angles are supplementary, then the lines are parallel. And I just read theorem 3.6 to you. So are these two, 1 and 2, are they supplementary? Yes, right? Are they consecutive interior? Yes. So we can say by theorem 3.6, A and B are parallel. That makes sense? All right, cool. Good. I was wondering if you guys are still there. All right, so, yeah, I know. All right, so we're going to do a little bit of a proof here. And this proof, the way they've set it up, is called a paragraph proof. Okay, so you know how we've been doing proofs. We started to learn how to do proofs. This is kind of in a written out form. Generally, we see proofs written out in the other form, but we're gonna work through this. If you would prefer your proofs written in a different format, that's okay too. So I might actually write my steps off to the side here too. All right, so this is going to be fun, right? In the figure, we have A is parallel to B. Okay, so we're looking at this picture right here. This is our picture of the day. We'll outline it in red. Okay. In the figure, A is parallel to B, and angle 1 is congruent to angle 3. All right, so angle 1 is congruent to angle 3. Prove that X is parallel to Y. This sounds like a fun challenge, right? Is everybody excited? Woohoo! So we know that A is parallel to B, and if I can draw it on here, I will. Remember, you can draw these little arrows here. Oh, I saw a thumbs up from Jake. All right. We know A is parallel to B. Remember, if we draw those little arrows, that's what that means. We know that angle 1 is congruent to angle 3, and we want to prove that X is parallel to Y. So before we get into all this stuff, let's just kind of think about how we can eventually prove that X is parallel to Y. Okay? So X is parallel to Y. So if we look at X and Y, and I'll erase these off of here. Here's X and here's Y. Okay? So a couple things. I could prove that X is parallel to Y if angle 1 is congruent to angle 2. Okay? So X is parallel to Y if angle 1 is congruent to angle 2. Why is that? What theorem or postulate tells me that that's true? Yes, so somebody said consecutive angle theorem. I like it, except they are not quite consecutive interior angles. They are corresponding angles, right? So I think that's what you meant. So they're corresponding angles, right? 1 and 2 would be corresponding. And so we'd actually have to use postulate 16, right? So if our corresponding angles, 1 and 2, are equal, then we could say, no, don't let me say that. That's not true. If 1 and 2 are congruent, that just basically means that A and B are parallel to each other. That doesn't actually help us out with X and Y, right? So that doesn't help us out. All right, what we should be looking at if we want to see if X and Y are parallel are angles 2 and angle 3. I'm just testing you out, right, guys? Yeah. So do you see what I'm saying? Angles 1 and 2 only help us out because X is our transversal. So angle 1 and 2 help us out to prove that A and B are parallel. We're out to prove that X and Y are parallel. So to prove X and Y are parallel, we have to show that angle 2 and angle 3, what are angle 2 and angle 3? Angle 2 and angle 3 are alternate exterior angles, right? So if we can show that angle 2 and angle 3 are congruent to each other, that would show that we have alternate exterior angles that are congruent, and then that would show that X and Y are parallel to each other. Did I lose you guys, or are you still with me? Still with you? All right, good. All right. So it says, solution, look at the diagram to make a plan. Hi, Kirsten. Look at this diagram to make a plan. The diagram suggests that you look at angles 1, 2, and 3. You also might find it helpful to focus on one pair of lines. Okay. All right, so we're given, so this is written out in a paragraph form, right? But basically, we're given that A is parallel to B and angle 1 is congruent to angle 3. So first up, let's look at angle 1 and angle 2. Right? What do we know about angle 1 and angle 2? So I'm down here and this picture down here. Okay. We know we're just looking, we know that A and B are parallel to each other. Okay. And then if I look at angle 1 and angle 2, X is my transversal in this case. So I'm going to draw it in pink. Okay. X is my transversal. So what do I know about angle 1 and angle 2? I know that angle 1, right, is congruent to angle 2. Why do I know that? know angle 1 is congruent to angle 2 because of postulate 15. Okay, so if you go back and you look at your postulate number 15, it says, if two parallel lines are cut by a transversal, then the pairs of corresponding angles are congruent. Okay. So then, if angle 1 is congruent to angle 2, we have angle 1 is congruent to angle 3, and we have angle 1 is congruent to angle 2, then what's that property that lets us substitute one in for the other? The transitive property. Then we know that angle 2 is going to be congruent to angle 3, and we can prove that they're parallel. Okay, so this is kind of helping you plan out here. It's saying, look at angle 2 and angle 3. If angle 2 is congruent to angle 3, then we're able to prove that x is parallel to y. So let's get down to the bottom here and kind of fill in the blanks here, okay? So it says, it is given that A is parallel to B. So by the corresponding angles postulate, so by postulate 15, which is the corresponding angles, I really want to spell angels today. So by the corresponding angles postulate, we can say that angle 1 is congruent to angle 2. Okay. It's also given that angle 1 is congruent to angle 3. So we can say that angle 2 is congruent to angle 3 by the transitive property of congruence. Therefore, so if angle 2 is congruent to angle 3, which theorem or postulate tells us that x is parallel to y? Oh, so close. 15. It's not a postulate, it's a theorem. Okay. Remember, 2 and 3 are alternate exterior. So it's either going to be, what do you think? Is it going to be theorem 3.2 or 3.5? You can look. I got to vote for 3.5. Who else votes 3.5? All right, I got two 3.5s. I agree with you. By theorem 3.5, which is alternate exterior angles converse. So alternate interior angles are congruent, then the lines are parallel. So does that make sense to you guys? How we got there? Okay. Would it be helpful to see it in like a different proof form, or was that enough of a explanation? You good? Awesome. Okay, so we have one more theorem that's in this section that we didn't get to talk about yet. Woohoo! 3.7, theorem 3.7. It's called the transitive property of parallel lines. And this one makes total sense. We applaud you. Thank you. All right, so I'm going to make boring parallel lines here. We got one. I will make them different colors, then they won't be quite so boring. Make that one green. Okay, these are lines. All right, this is, we're going to talk about. Let's talk about theorem 3.7. Theorem 3.7. Okay, so we have three parallel lines. We will call them P, Q, and R. Okay, theorem 3.7 is called the transitive property of parallel lines. We've heard this word before, this transitive word, several times, right? Transitive applies when we have, like, when A equals B and B equals C, that means A equals C. All right, so all of a sudden we are going to apply this to parallel lines. So the transitive property of parallel lines says that if P is parallel to Q, all right, and Q is parallel to R, then P is parallel to R. So if two lines are parallel to the same line, then they are parallel to each other. So basically, theorem 3.7 is just a big parallel party, right? P is parallel to Q, Q is parallel to R, so sure, P will be parallel to R too. So that's 3.7, theorem 3.7. We don't even have any problems to do with that, so we are good. All right, so now we're going to move on to 3.4. We're going to do a little bit of 3.4. Before we start, let me look up this cheesy video that I'm going to play for you for 3.4. For some of you that have been in my class before, you may have seen this video. We are going to talk about 3.4 is talking about slope. So slope actually comes up in algebra. So this is kind of getting back a little bit to our algebra concepts, but slope is a really important math concept. It is Slope Dude. He's coming out. All right, let me find Slope Dude on YouTube. Slope Dude, YouTube. Yeah, it's Slope Dude. Okay, so what is slope? First of all, before I play you this awesome video that you're going to be so excited about, okay? What does the slope refer to? Slope refers to a line, right? So we have all kinds of lines. These lines just happen to be horizontal lines, but we have all kinds of lines, and the slope basically tells you how quickly or slowly your line is, basically the change in how fast it's moving up versus the change in how fast it's going sideways. So the change in the rise over the change in the run. Slope is one of those concepts that gets covered in Algebra 1, geometry, Algebra 2, pre-calculus. Slope, you cannot get away from slope. So you get to hear slope again. And for my friends that have had class with me before, you've seen Slope Dude. If not, here is your exciting 2 minutes for the day. So I just want to make sure when I change over to YouTube, can you guys see it before when I was changing over? Here, Sophia, can you see it now? Okay. All right, here we go. This is how you're going to remember the slope. All right, how awesome was that? Wasn't that amazing? I know. Now you guys can't ever forget the slope. I didn't notice it the first time I played it, but listening to over headphones, I noticed the nice music. Oh, there was sound. You didn't get any sound? Oh man, I'll have to send you the YouTube video so you can enjoy it. Nobody heard it? Oh no, nobody heard it. Well, then that's no fun at all. You missed the guy's voice. I'll have to send it out after class. You have to redo it. I don't know how to make sure that the sound is working. It was all the way turned up, so I'll have to send it out to you. Or I can recreate it for you. How's that? I'll recreate it for you for a minute. But I don't have as good a voice, but I will send it out at the end. All right. So basically, there's this guy. His name is Slope Dude. Okay. Slope Dude represents how we think about the slope of a line. Okay. Slope Dude is awesome. So the first thing that Slope Dude is going to do is he's going to go skiing. All right. And when he skis, he always skis this way. He always skis from left to right, just like you read. So it should be able to remember. All right. So first, the Slope Dude is going to go up the hill. Okay. Yes. Thank you. Someone remembers from last year. So when he's going up the hill, he's going puff, 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 because it's really hard to get up the hill. And so he's going puff, puff, positive, puff, puff, positive. So when we have a positive slope, okay, slope is a number. When we have a positive slope, that means that we're going up the hill. Puff, puff, positive, puff, puff, positive. Okay. Then he gets to the top of the hill here, and he's going to ski down the hill. Okay. Now this is where it gets exciting. He's going down the hill and he's saying, nice, nice, negative. Nice, nice, negative. Yes. All right. Because it's nice to ski down the hill because you don't have to work hard, right? Nice, nice, negative. Nice, nice, negative. Okay. All right. Then he's going to get to the bottom of the hill. I have a slope dude expert on the call. Yes. So he gets to the bottom, right? The slope skier dude gets to the bottom and it's flat. And it's really hard to ski when it's flat. So he says this is zero fun. This is zero fun because it's flat. It's zero fun. And then the best part of the video is when he gets to the end. Okay. Yes. And this is what the guy says on he says this on the YouTube video. He says he falls off the cliff, and as he falls off the cliff, he says the worst curse word in algebra, which is undefined. But it's way better if you watch the video, so I will send it out to you guys. All right. So this is just a very, very cheesy way to help you remember what the slope means in the coordinate plane. All right. So when you have a slope that is rising, like you're going up a hill, right? When you have a slope that's rising from left to right, then it's a positive slope. When you have a slope that is falling from left to right, you have a negative slope. When you have a line that is completely horizontal, then your slope is 0. And when you have a line that is vertical, then that's undefined, not unrefined, undefined is what that should say. I try to spell it right. Defined. I will send that to you so you can hear it in all its awesomeness. All right, so then if you switch back to your notes, you guys should be experts and should be able to fill all these in really quickly. All right. So let's start with positive slope. A positive slope. Okay, so which of these lines has a positive slope? We've got Y, K, X, and J. K has a positive slope, right? So it's going up the hill, basically, right? It rises from left to right. Okay. Our negative slope, nice, nice negative, right? Yes. Yes, your negative slope is J. Sorry, I can't see my. And that's going down the hill. So it's falling down the hill. It's skiing down the hill. Right? All right. Where's the worst thing that could happen to you as you're undefined? Your worst thing that could happen? Oh, that's a good guess. Oh, it is. Yeah, no, it is an N. You're right. I was calling it Y, but Y is my Y-axis. You're right, Sophia. It's M. So this is undefined is where we have our vertical line, right? And then our skiing where it's really, really hard. This is zero fun. This is zero fun. That's our line that is L, right? And that's when it's horizontal. Okay. And then the other thing up right at the top of your page, I kind of cut it off, but at the top of your page, let's make it a little bit bigger. We have the word slope. So we're going to define it in geometric terms. So slope is the ratio of the vertical, cannot spell today, the vertical change, the rise to the horizontal change, which is the run. Slope is the ratio of the vertical change, the rise, to the horizontal change, the run. All right, so let me see if I have, let me put Desmos up on here. All right, so let me put a couple little, y equals, just give me 1 second here. I'm going to pull this over to Paint. All right. That's that. This is Paint. I can draw on this. Okay. So I have some lines here. You can see I have a red line and a blue line. Let's talk about what that slope actually means. Okay. So you can see that I have a coordinate plane here, an X and a Y. So slope refers to how quickly a line is rising or falling. All right. So for this red line here, is the slope going to be positive, negative, 0, or undefined? Is it puff, puff positive for the red line, nice, nice negative, 0, or it's positive, right? All right. In addition, I just want you to see visually how you can actually think about what slope means. All right. So what slope means is if I start at one point on my ski hill, right down here, and I go up to another point up here. Okay. So what the slope means is I'm looking at how the change in my vertical, so vertical means this way, right? The change in my vertical, the change in my rise. So I'll put a couple words on here. The vertical change, or the rise. Some people do rise over run, right? Or your change in Y. All those mean the same thing. So to ski up my hill from here to here, okay, I went up, this is 1, 2, 3, we'll say we go up 3 feet. Okay, we'll call this feet. So my change in my Y's, my rise is 3 feet. All right. And then I look at the rise, and it's the ratio of that over my run. So my run is going to be right here. All right. So we call this the run, or the change in the horizontal, or your change in X. Okay. So when I am skiing up my hill, okay, skiing up my hill, I go up 3 feet, I rise 3 feet. Every time I run 1 foot. All right, can you see how this only goes 1 unit? So the slope of this line would be 3 feet over 1 foot, which is just 3. All right, so if I go up 3 and over 1, I get to my line. If I could keep going on my graph, which I can't because this is just a static graph. But if I go back to my Desmos graph, if I have it somewhere. Oh, here we go. Let's go the other way. All right. What's another way to write a slope of 3? Or 3 over 1. We could also write it as negative 3 over negative 1. Okay. Would you agree that these two are the same? 3 over 1 and negative 3 over 1 are the same? Because they just cancel each other out, right? So another way I could look at this is if I'm going down the hill, Let me change my colors here. So I'm going to look at this -3 over -1. Okay. I rise -3. So I go down -1, -2, -3. I rise -3, and then I run -1, and I'm still on my same slope. Okay, have you guys all seen this before? Yeah, one person's seen it. All right, cool. So let's do one more. Let me clear this off and take another screenshot. Oh, I know. Gotta find where it's at. I think this is a really important concept to understand, so I just want to make sure that we give it a lot of attention here. Okay. Because like I said, it does show up. It keeps showing up. Slope just doesn't go away. Okay, so I have another line here. Okay. Is the slope of this line positive or negative? What do you think? Negative, right? It's going down the hill. Nice, nice negative. All right. So if I want to actually physically look at this and figure out what my slope would be, I'm going to pick a point here at 0. Okay. And let's see. It looks like it intersects the graph right here. Okay. So I'm going to pick those 2 points. All right. So remember, my slope is my change in my y over my change in my x, or my rise over my run. Okay. So for this particular case, if I go up 2 spots, all right, so my change in my y is 2. Okay. Then to get to my next spot on my line, I have to go to the left 1, 2, 3. But I'm going to the left, not to the right. So you can see here, I'm going up. So you know that's positive, right? But when I go to my left on my graph, that's actually traveling in a negative way. So I go to my left, -3. My change in my x, my run, is this. Okay. So when I compare my change in y to my change in x, I would say that the slope of this line is -2 over -3. Okay. Another way you could write that is just -2 over -3. And like you said, Sophia, we know just by looking at the blue line that it's a negative slope. But you can see on here how you end up with a negative 2 over 3. So that means that for my next point, if I go +2, so I rise +2, and I run -3, I get to my next point on my graph, right? And then down here, I'm kind of off the screen. Let's see if I can go any further down this way. It's almost off the screen, but we'll still do it. Okay. So if I rise, well, actually, let's do it a different way. So we have -2 over 3. We can actually put the negative on either side. Okay. So I have 2 over -3. I could also write my slope as -2 over +3. Okay. So what does this mean? If I start here and I go -2, that means I go down here, right? And I go +3, I'm off my screen, I know, over here, +3, then I end up at the same point on my line again. So you can see how the slope could be kind of written in a different way, but that negative sign either applies to your rise or your run. All right, so that is slope. We are going to do a lot more practice with slope on Monday, but I just thought it would be helpful to kind of give ourselves an overview and to watch that awesome video. So I will send that out to you guys. Keep working on your Chapter 2 test, and we're going to keep going with Chapter 3 on Monday. All right. Thanks, guys. Have a great day. See you later.